It can sometimes feel like the world is just random. But what if I told you there are secret rules that govern chance itself? In this explainer, we're going to pull back the curtain on the simple math behind probability. Let's get into it. Have you ever been playing a game and thought, wait a second, is this actually fair? It's a great question, but instead of just looking at a game that already exists, we're going to do something better. We're going to build our own, right from scratch. That way we'll really see how probability works from the inside out.
And our only tool is going to be this, a simple six-sided die. It doesn't look like much, right? But this little cube is a powerhouse when it comes to probability. For the next few minutes, this die is our entire universe. Let's see what it can teach us.
Okay, so before we can figure out the odds of our game, we need to understand the most basic action. What is the one thing we do over and over? Well, in the world of probability, that action has a special name. It's called a chance experiment. And honestly, it sounds way more complicated than it is. It's just any process you can repeat, where you know exactly what could happen and where each try doesn't affect the next one. So every roll of the die is a fresh start. Simple as that.
So, yeah, rolling our die is the perfect example of a chance experiment. Same with flipping a coin. But it can be weirder stuff too. The source material mentions that even just tossing a paper cup to see how it lands counts. So these experiments are happening all around us.
All right, so we've got our action, our chance experiment. The next step is to figure out everything that could possibly happen when we do it. We're basically creating the blueprint for our entire game. And that blueprint? It's called the sample space. The name says it all, really. It is the set of every single possible outcome. Not some of them, not most of them, all of them. If it can happen, it's in the sample space. For our trusty die, the sample space is just 1, 2, 3, 4, 5, and 6. That's it. Nothing else can happen. It's a completely closed system, and that's what makes it so perfect for getting a handle on probability. So we know what can happen, but the real question is how likely is any of it? Turns out there are two main ways to figure that out. We can either learn from experience or we can use pure logic. Let's see which one is better for our game. So let's ask a classic question. What's the chance of rolling a 6? I mean, we could just roll the die 1,000 times and count how many 6s we get, but there's got to be a smarter, faster way, right? And here are our two paths. On one hand, you have estimated probability. That's the one where you actually collect data. You roll the die over and over, and the more you do it, the closer your results get to the real answer. On the other hand, you have theoretical probability. This is all about the model. You don't need to roll the die at all because you calculate what should happen in a perfectly fair world. So which one do we need? Well, since our goal is to build a fair game from the very beginning, we can't rely on messy, real-world data. We need the clean, precise answer. We need theoretical probability. And here's the best part. The formula for this is incredibly simple. It's like the engine that makes fairness work in any game of chance. And we're about to pop the hood and see it for ourselves. And there it is. The probability of something happening is just the number of ways it can happen divided by the total number of things that could happen. That's it. It's so simple, but it is unbelievably powerful. Okay, let's take our new formula for a spin. What's the probability of rolling a number that's greater than 4? Just think about it for a second. What are the favorable outcomes, and what's the total? Let's walk through it. We know there are 6 total outcomes. And how many of those are favorable, meaning greater than 4? Well, that's just rolling a 5 or a 6, so 2 favorable outcomes. That means our calculation is simply 2 divided by 6, which, of course, simplifies to 1/3. So there you have it. There's a 1 in 3 chance of rolling a number greater than 4. No guesswork, no experiments, just a little bit of math. Okay, that was pretty straightforward. But real games are rarely that simple, right? So what happens when we start combining things? Let's add a little twist to our game. What if to win, you had to roll the die and flip a coin? Now we're dealing with 2 things at once. This is what's known as a compound event, and this is where things get really fun. Now, when you have more stuff going on, it can be easy to lose track of all the possibilities. That's why a tool like a tree diagram is so helpful. It's just a simple way to map out and visualize every single outcome. We can use the same idea from the example on screen for our coin and die game. Let's imagine building one right now. You start with the first event, the coin flip. So you have 2 main branches, heads and tails. Then, coming off of the heads branch, you draw 6 little branches for the numbers 1 through 6, and you do the same thing for the tails branch.
And just like that, you can see all 12 possible combinations, from heads 1 all the way to tails 6.
So, what does this bigger sample space tell us? Well, now we can answer harder questions. For example, what's the probability of getting heads and a 6? Looking at our tree, there's only one path that gets us there, out of 12 total paths. So the probability is 1 out of 12.
So, let's do a quick recap. We've put together a pretty great probability toolkit. We know a chance experiment is the basic action. The sample space is the list of everything that can happen. The probability formula is the math we use to calculate the odds, and compound events are just what happens when you mix them together.
You've basically learned the secret rules of chance. So next time you're playing a game, or even just wondering about the weather, you won't just see randomness. You'll see the numbers behind it. So take a look around. What are the odds at play in your world?